is Lamia, and I'm majoring in Aerospace Engineering.
I'm Brian Winsey, and I'm an Aerospace Engineering major.
Hello, I'm Vinny, and my major is in Aerospace Engineering.
Hi, my name is Tristan, and my major is Aerospace Engineering.
Hi, my name is Adrian Paggi, and I'm majoring in Mechanical Engineering.
And I'm Ryan Draskovich, and I'm majoring in Aerospace Engineering, and we are the High-Speed UAV Gold Team. The objectives for this project was that it must be a clean sheet aircraft. It must be highly maneuverable and high speed with a maximum speed of 160. It must also navigate through a pylon racing course and have retractable landing gear. There were no outside sponsors for this project. Our team chose this project because it was an innovative project and new to UCF, one that had never been done by a senior design team in the past. We also thought it would be a fun way to apply our coursework knowledge learned throughout our undergraduate career to a practical real-world application. Additionally, some of the broader impacts that could be seen from this project is that it could get new RC hobbyists into the field, as planes that typically fly at the speeds we were targeting can cost upwards of $800. Additionally, this work done on the team would serve as a benchmark for future senior design teams.
These are the most recommended airfoils for model planes. An XFLR5 analysis indicated that the PSU airfoil was the most efficient. With a higher CL over CD ratio over a range of angles of attack and Reynolds numbers, it can generate the highest lift at the expense of producing drag. But with more research, we found out that our plane didn't really require a high lift coefficient. Since lift is a function of velocity squared, our high-speed plane would generate lift very easily. In fact, in order to cruise a plane of about 1.5 kilograms at 120 miles per hour, the PSU airfoil, which has high lift coefficient, would require a very small wing area, or to be mounted at a negative incidence angle, which are both not ideal for plane design. The best alternative solution we found was to use a symmetrical airfoil. The best one we found was the SD8020, which has both low drag and lift coefficient values, and would allow us to fly at slough at 120 miles per hour with a small incidence angle. We decided to continue with the SD8020 as our airfoil of choice.
After the team had decided on an airfoil, we then created an iterative MATLAB code that would determine the best wing size possible. To do this, we took 2D CL data generated from XFoil and transformed it using a lifting line approximation into 3D CL data. We then calculated the lift, the drag, and induced drag to get a total drag value for each combination of chord length and span length. From this, we would then calculate the power and energy using the time it would take to fly the course. The code would then compute all different possible combinations and give us the total power values for each combination. We then picked the lowest power with that combination.
To decide a taper, we took multiple taper ratios and compared the asphalt efficiency to that of an elliptical wing in XFLR5. After analysis, it was determined that a 41% taper ratio was the most efficient platform.
To determine the length of the fuselage, we used a relationship table found in Raymer's aircraft design. This related the fuselage length to our initial weight estimate. We also analyzed different planforms of the fuselage and threw them in ANSYS to analyze the drag values. In the end, we ended up going with a hybrid fuselage design, which had the second lowest drag value to the teardrop style fuselage. The width and diameter of the fuselage was minimized to only house the necessary electrical internals, and the upsweep angle was set to 10 degrees to minimize the form drag.
So for the control surface sizing, the aileron is supposed to be around 20% of the wing chord, which comes out to 0.0326 meters, and the aileron span is supposed to be around 60% of the half span, which is 0.3085 meters.
The next step is to have an initial estimate of the total drag buildup of the plane at cruising conditions. We did that by running a CFD simulation for each of the four main components: the fuselage, wing, horizontal, and vertical stabilizers. They were all separately simulated in an airflow of 120 miles per hour using ANSYS Fluent. Here the pressure distributions are shown, which is directly related to the force exerted on the surfaces. We found that the fuselage creates 1.8 newtons of drag, the wing 3.5, the horizontal stabilizer 0.8, and the vertical stabilizer 0.3, which adds up to a total of 6.4 newtons of total drag.
For the propulsion package, eCalc software was used to select both battery and motor. The thrust necessary to overcome drag at 120 miles per hour would be provided by an 8x6E propeller from APC. The resultant propulsion system would be two 5,000 mAh batteries, a Scorpion 1040 kV outrunner motor provided by UCF, and the previously stated 8x6 propeller.
Now, using a more accurate model, the team was able to perform a more realistic CFD of the entire aircraft. Using StarCCM for a higher mesh quality, the team estimated the new drag buildup of the entire aircraft to be 11.7 newtons, which is higher than our initial assumption. By analyzing the pressure distribution over the surfaces, we can see that the main areas of high pressure, and therefore areas of high drag contribution, are the front face, wing mounting, leading edges of the lifting surfaces, and where the servos and connectors are. If we look at the cross-section view of the pressure plot, we can clearly see that trend, especially at the wing mounting and tail dragger landing gear locations, where the design could be more streamlined. However, the added complexity of retracting the tail gear or losing benefits of having an easy-to-mount modular wing design is not worth the possible additional gains in aerodynamics. And here is a nice demonstration of the entire flow around the aircraft, shown at a cruising speed of 120 miles per hour on StarCCM.
For the structural design of the plane, the team decided to do different materials for different parts of the plane. For the fuselage, we decided to go with a 3D printed fuselage for ease when it comes to building complex geometries and time constraints. For the wings, we decided to go with a foam wing with a carbon fiber spar across it, going from tip to tip, as it was lightweight and provided great strength. On top of that, we covered the wing in laminate wrapping to keep everything together. The tail was done in a similar manner, just without the laminate wrapping.
After the structural designs were determined and a full CAD was created, the team used ANSYS to perform FEA and test the forces that would be seen during in-flight conditions. The first test that was conducted was an FEA test of the wings. As you can see from the video, the deflection reaches a maximum at the tips of about 2.7 centimeters. The following also shows the stress located in the wing. The next test that was performed was comprised of a full-body FEA. The vertical stabilizer and 10mm laminate wrap were omitted during this analysis, as the primary analysis point would be the fuselage and how the forces would act on it during slough conditions. As we can see from the video, the stress distribution can be seen. Additionally, the factor of safety can be shown reaching a minimum at around the bolt holes. Using this feedback, the team decided to implement washers to go around the bolt hole to further spread out the distribution of forces. A drop test was also conducted using ANSYS explicit dynamics. To stay within the node limit, a coarse mess can be seen on the horizontal stabilizer. This video illustrates the strain seen in the tires during the drop. Additionally, the factor of safety in both the metal and plastic parts can be illustrated. The factor of safety reaches a minimum of about 3.7, which proves that our factor of safety is within the recommended limits of 1.5.
So we approximated an elliptical slough flip distribution and approximating a 14 newtons elliptical distribution on foam, spar, and 10mm film wing using weights. We got a total experimental deflection of 2.25 centimeters, which was pretty close to the FEA deflection of 2.97 centimeters. For the RPM test, we used a tachometer and a scale and measured the static thrust versus RPM. For the wingtip test, we fixed the ends of the wings with 2 stands and loaded a with 25 pounds. Preliminary flight test, the front part of our fuselage broke at full throttle, so we secured the firewall and did a full throttle test.
To begin manufacturing, we first 3D printed a fuselage, then created the wings. To create the wings, we wire cut our wings and wire cutted a spar hole that ran down from tip to tip. We then laminate wrapped it and did the tail in a similar manner, but used the wire cutter at UCF, which was controlled by a CNC machine. After the wings and tail were mounted to the fuselage as well as the motor, we made cutouts for the servos and retractable landing gear. After everything was wired together properly, we had a working plane. No, that's.
Yeah, dude, let's. Dude, it's a rock.